All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.
Good morning, everyone. How many of you are knowing about the activities which we are observing in the daily life? As far as the optics, which is one of the branch of physics, is concerned, we could be able to know all the things which are happening into our daily lives, why it is happening, and what is the reason behind this phenomenon. We'll be able to understand more in detail about it. In continuation to our earlier lectures, today we'll be focusing on one of the important phenomena of optics, that is diffraction. Myself, Professor Nitin Puri, who will be taking the lectures on the optics. Welcome to S-Chance Academy. Today we'll be discussing about the Fraunhofer diffraction at a circular aperture, which normally relates to the topic which we had covered in the previous lectures when we had started with the Fraunhofer diffraction at a single slit. And we could be able to know what are the basic observations onto the screen, what type of pattern we'll be observing onto the screen with the help of the diffraction at a single slit. And we were discussing that what type of intensity pattern normally we observe it in the case of single slit. Now, in continuation to that, we'll be focusing on the Fraunhofer diffraction at a circular aperture. If you want to go more in detail about these topics, you can go to the ebook link which is available onto the screen in the description box. So, as you know, we will be talking about the Fraunhofer diffraction at a single slit, and in that continuation, we'll be discussing about the Fraunhofer diffraction at a circular aperture. Now, when we are talking of the slit, in the previous sections, we had taken a width and but now in this case we had taken the width of the slit and light was incident onto it when we had taken the case of single slit. Now in this case, Fraunhofer diffraction at a circular aperture, what we are doing it, AB is considered to be a, like if you see this, A and B is a circular aperture, right? And it is having a diameter of, this is D, right? This is D, right? Now, C is the center of the aperture, right? C is, if you see this one, this is C, we are considering at the center of the aperture, right? So, AB is the aperture, circular aperture we are talking. D is the diameter, right? And if C is the center of the sequence and P is the point onto the screen, suppose we are putting a screen over here and we are considering a point P here onto the screen, we are considering it as the screen, SCREE, right? So CP is, normally we are saying that CP is the perpendicular onto the screen. This CP, if you see this one, right? Now CP is the perpendicular to the screen. So if you just summarize this particular part only, we are having the AB, which is a circular aperture, D is the diameter, right? And we had mentioned the circular aperture as AB, right? There is the screen, there is the point P, and we had put a perpendicular CP, right? Now, The screen, what we are considering, that screen is perpendicular to the plane of the paper. Screen is perpendicular to the plane of the paper, right? And a plane wave, we are considering it as in this way. If you see this one, a plane wave is incident onto this, right? So a plane wavefront is incident on a circular aperture, right? Now the secondary wave traveling in the direction CO comes at a focus of P dash, which we are observing it onto the screen, P. So the secondary wave, what exactly it is? The secondary wave traveling in the direction CO comes to the focus at P. Now if why we are saying so, suppose we are having, now we are putting a lens L, right? So if I just draw it, now if we are going in this direction and then it is focusing at point P, and then right, and then if we are plotting in that way, and then it is reaching to point P1, right? So now let me draw it first, then we can just understand in detail about all these things. Just wait for a minute, and then if we are coming in this way, or coming onto the screen, and then it is reaching to point P1, right? And then one more angle, if we are putting it in that way, I'm just discussing it with all of you. This is reaching to point P1. This is angle we are saying theta, and this angle also we are saying it as theta, right? This is the direction we are talking of right now, right? This is not this one. This is the perpendicular one only. So this is a wave showing the direction, right? So and then these all are the waves which are coming and reaching to the screen, right? And this is, if we are putting all the points, because C is the center point, C is the center point, and we are putting a perpendicular which is from C to, this is AD, right? Okay, so if you see onto this screen right now, what is there? If you see this one, this is, I'm putting this as O, right? This is angle theta, this is P and P1, the distance P and P1 is X, right? See, so what is happening? AB is the circular aperture of a diameter small d, right? C is the center of the aperture, right? We can see here, right? And then P is the point onto the screen, we have the screen, right? CP is perpendicular, this CP is perpendicular to the screen, right? And screen is perpendicular to the plane of the paper, right? Okay, and a plane wavefront, you can see here, a plane wavefront is incident onto this aperture which we had considered AB, where C is the center point and D is the diameter, right? So the secondary wave traveling in the direction CO comes in the focus at point P. So what is P? P is considered to be the position of the central maxima. You see, we are observing the central maxima at point P. CP is the perpendicular, right? So when we are considering the position, it means this point P is the position of central maximum, right? So all the secondary waves which are emanating from the points equidistant from O, they travel the same distance, right? And before reaching to point P, right? Before reaching to point P, and therefore they reinforce each other, correct? So when they are reinforcing each other, now what is happening? Let us consider the secondary waves traveling in the direction which is inclined at an angle theta, right? if you see here, this is angle theta. What we are considering that the point are not coming from here, but they are going in the other direction as well and making an angle theta, right? So let us consider the secondary wave traveling in the direction which are inclined at an angle theta degree, right? And with the direction CP. So it means CP, we are saying that CP is the direction, right, which is perpendicular. So we are saying that the other waves are going in the direction making an angle theta, right? So if it is making an angle theta with the direction CP, so all these secondary waves, they are meeting at point P1 onto the screen. See, we are now making a statement that when they are not making an angle theta, they are meeting at point P, because CP is the perpendicular, right? And we have made a lens, right, because it's the convex lens which is making the maxima and minima which we are observing onto the screen. This is the lens, right? So the another points we are considering is at making an angle theta degree. So all these secondary waves meet at P1 onto the screen, and this P1 is a distance, the distance between P and P1 is small x, right? So part difference between the secondary waves emanating from point B and A. What is B and A? This is B and A, right? We had considered this AB is a circular aperture having a diameter small d. So what we are saying that because as I said it that when light is incident onto it, according to Huygens principle, all these points will work as a point source. So we'll be having the secondary waves which are emanating from these point sources, and we are observing the interference between the waves which are coming from these secondary sources, right? So what we are saying, we are observing the interference from point A and from point B. We are considering the extreme points, this A and this is B. So what we are saying that the path difference between the secondary waves emanating from point B and from point A, right? Because these are the extremities of the diameter, right? These are the B and A are considered to be the extremities of the diameter, right? And what we are saying that suppose it is AD, right? So what exactly? So if we are considering it in the triangle, if we take a triangle ABD, we have drawn a perpendicular. This is BD, right? This is BD, right? So if we see onto this one in a triangle, if we say the triangle A, B and D, if the triangle ABD is there, right? So what will be the AD? AD will be equal to, what it will be? It will be equal to d sine of theta, right? It is d sine theta. So what exactly it means? The point P1 will be of minimum intensity if the path difference is equal to the integral multiples of lambda, right? So I repeat it because it is important to understand the point P1 onto the screen. Here is the point P1 which we are talking of right now. P1 will having the minimum intensity if the path difference is the integral multiple of lambda. What does it mean? It means we are saying it that d sine theta is equal to n lambda. D sine theta is equal to n lambda. D sine theta is equal to n lambda. And the point P1 will be of maximum intensity, right? Right. So if what exactly we are talking? We said it that d sine of theta, if we are saying the nth one is equal to n lambda, this is n lambda, right? This is, we had done it last one, right? So the point P1 will be of maximum intensity if the path difference is equal to the odd multiples of lambda by 2, right? So what it will become like, look like, it will be equal to d sine theta n. D sine theta n is equal to, d sine theta n is equal to, what it will be? It will be equal to 2n plus 1 lambda upon 2. So what we are getting here, the two equations we got it. The point P1 will be of minimum intensity when the path difference is an integral multiple of lambda. But the same point P1 will have the maximum intensity if the part difference is an equal to odd multiple of lambda by 2. So therefore d sine theta n is equal to 2n plus 1 lambda upon 2. So P1, if the point of minimum intensity, P1 what we are considering, suppose this is, we are saying this is equation number 1, this is equation number 2, which we are getting it in terms of minima and maxima at point P1, right? So if P1 is the point of minimum intensity, then all the points at the same distance from P as P1 and lying onto the circle of radius x will be of minimum intensity, right? What I mean to say that if P1 is the point of minimum, what exactly, because the same we are doing it. If you're watching in the previous screen where we had talked about it, that we have a circular aperture of diameter d, light is incident onto it, every point is working as a secondary source, the light is secondary wavelets are emanating from it, and there we are getting the maxima and minima intensity is observed onto the screen at point P1, right? And what we are saying it, that all the points we had considered the extremities of the diameter, for that extremities of the diameter A and B, and we are observing that they are not reaching directly perpendicular, which is perpendicular to the plane of the paper, but they are making an angle theta degree, right? So what we are saying, that the part difference from the secondary wavelets from A and B we are observing, right? So we had observed it that AD, which is in the triangle ABD, we have seen it that it is equal to D is equal to D sine theta. Then we said it that if P1 is of minimum intensity and maximum intensity, they will be equal to D sine theta n is equal to n lambda. And if it is of maximum intensity, the part difference is equal to the odd multiples of lambda by 2. So what we are saying, that if P1 is the point of minimum intensity, then all the points at the same distance from P as P1 and lying on the circle of radius x will be of minimum intensity. This is one part. Second, therefore, what exactly the diffraction pattern will be observed? So diffraction pattern due to a circular aperture is consisting of a central disc which is called an airy disc. What it is called? It is called AIRY, airy disc. It is called an airy disc, right? So now the points when we are talking of airy disc and how it is related with the Fraunhofer diffraction from a circular aperture, we'll be discussing after the break. So I just want to putting it up a question in a way which I'll ask it after the break, that why this airy disc will play an important role in terms of observing the maximum and minima onto the screen with the help of the circular aperture. So we'll meet after the break.
Hi, I'm Dr. Sujata Sengupta. I'm going to be teaching you all about organic chemistry, all those different topics, stereochemistry, alkynes, which you found very difficult, that I will be discussing with you. So please hit like, share and subscribe, and always come back to S. Chand Academy for more videos in the future.
So now welcome back to the S. Chand Academy, where before the break we talked about it, that what exactly the minima and maxima we are observing onto the screen due to the circular aperture. And in that continuation we talked about it, that we have what we are having, we have a circular aperture, we have a screen, we have a lens, light is emanating onto it, every point is working as a secondary point source, and then those point sources are having interference between the two, among the two. We had considered the extremities of the diameter A and B, and those extremities of the diameter we are observing that what type of pattern we are observing onto the screen. So we had observed it that we are getting two equations, 1 and 2, which is d sine theta n is equal to n lambda, which is showing the minimum intensity if the part difference is an integral multiple of lambda, and we'll be getting the maximum intensity if the part difference is an integral multiple of or odd multiples of lambda by 2. So these equations 2 we got it. We said it that if P1 is a point of minimum intensity, then all the points at the same distance from P as P1 and lying on a circle as small x will be of minimum intensity, right? So what we got it, that the diffraction pattern due to a circular aperture will be consisting of a central disk, which we discussed it as the Aery disk, which we stopped it before the discussion, before the break. And then when we are coming on to this one, what we are saying it, that it will be surrounded by dark and bright concentric rings. Concentric means the center will be having the same, but we'll be having the dark and bright rings we are observing, right? So what this type of rings are called? They are called Aery rings, right? So Aery disk, we had talked about it, and we said it that Aery disk, it will be surrounded by dark and bright concentric rings, which is called Aery rings, which is called Airyngs, Aery rings. So this is Aery disk, and we are talking of Aery rings, and it is important to note that it will be concentric, bright and dark rings we are talking of right now. I hope it is clear to each and every one of you. We are talking of that with the help of Aery disk, which will be surrounded by alternate dark bright concentric rings called Aery rings, right? So the intensity of that dark rings, is 0. The intensity of the dark rings is 0, and that of the bright rings decreases gradually towards or outwards from P. Repeat it again because it is important. We are talking of the Aery disk, we are talking of the Aery rings, and we are talking of the concentric bright and dark rings as well. So what the point we are discussing, that the intensity of the dark rings is 0, right? And that of bright rings, it is decreasing gradually outward from P, right? So it means when we are going away from point P, the intensity of the dark rings is decreasing gradually, right? So what exactly we can say? So it means if the collecting lens is very near to the slit, right, then, or when the screen is at a very large distance from the lens, right? These are the 2 points I'm making right now. What are the one? If the collecting lens is very near the slit, or when the screen is at very large distance from the lens, at that particular point, what is going to happen? This is if I see this one, this is sine theta. Sine theta will be equal to theta, and it is equal to x upon f, right? X upon f, right? Correct. So it means what exactly we want to make it right now, that for a secondary maximum, sine theta is equal to x upon, it is x upon f. We got it, right? And the secondary, for a first secondary minimum, we said it d sine of theta is equal to lambda, right? D sine theta is equal to lambda. Therefore, sine theta is equal to lambda upon d. Correct? So if this is suppose we say this is equation number 3, suppose we say this is equation number 4. When you are equating the equation number 3 and equation number 4, what we are going to get it? We are going to get it that x upon f is equal to lambda upon d, right? So what we got it, these are the 2 equations. If we are equating sine theta is equal to x upon f, and sine theta is equal to d sine theta is equal to lambda, and when theta is very small, at that time sine theta is equal to lambda upon d, which is equation number 4. And then 3 and 4, if we are equating it, we got it x upon f is equal to lambda upon d. So what will be the value of x? So the value of x comes out to be f lambda upon d, right? This is f lambda upon d, right? So where x is the radius of the Aries disk, number one. Number two, but what exactly actually it is happening? The radius of the first dark ring, right? The radius of the first dark ring is slightly more than given by this equation sin theta is equal to lambda upon x is equal to f lambda. This is, suppose this is isko, let me clarify in that way. This is suppose equation number 5. We said it that x is the radius of the Aries disk, right? But actually the radius of the first dark ring is slightly more than at is given by equation number 5. According to Airy, it is given by x is equal to, this is given by x is equal to 1.22 f lambda upon d. This is according to Airy, according to, if we say it according to Airy, ACCORDI, according to Airy, x is equal to 1.22 f lambda upon d, right? So the discussion on the intensity distribution of bright and dark rings is similar to the one given for a rectangular slit, right? This is what exactly it is. So with increase in the diameter of the aperture, the radius of the central bright ring decreases. This I repeat it again. With increase in the diameter of the aperture, the radius of the central bright ring decreases. So what exactly we had concluded in the Fraunhofer diffraction due to a circular aperture is that, what exactly we had seen it right now, that we could be able to see that if we have a circular aperture of a diameter d, we had a screen, we had a lens of focal length f. We know that when light is incident onto the screen, every point is working as a secondary source, and those sources are having an interference among the two, right? So we had considered that we are observing the pattern onto the screen, and we had seen that if we are considering the central maxima at point P, so when light is incident onto it, so what exactly we are going to get it in this Fraunhofer diffraction at a circular aperture. We have a screen, we have a lens, we have the circular aperture, light is incident onto it, and we are observing the intensity distribution onto the screen. So with the help of this expression which we had covered completely, what exactly we had concluded that with the increase in the diameter of the aperture, the radius of the central bright ring decreases. So if you want to go more in detail about it, you can go through the book, ebook, whose link is available onto the screen and the description box. Thank you so much. If you would like this lecture, please like, share and subscribe this channel. Thank you.